In principle, it's cumulative, but in practice, it emphasizes the stuff at the end of the course. Okay, we're back on the air. So, here are the results from the midterm exam. This is the morning session, that's you. And so that's the live feeds. This is the afternoon session, that's just a regular class. And these people are feed people who take the course only through this CDs. Same thing here, this continuation. So it looks like the afternoon people did better on average. The assertion being that represents the fact that they're more awake in the afternoon. I don't know if that's true or not. You can see, though, that there's really not that much difference between the two columns. Feeds is a much smaller sample. So, I don't know, it looks to be pretty much the same, although I would say that these people, on average, are a little bit lower than the others. Notice that there were a couple of very high grades. 3 people got 35, 2 in this class, and, one in this class, and 2 in the afternoon class. And there was a 33, which was almost as good. And the grades tended to be in the middle. Well, here there seems to be more gaps, here it's more evenly spread out. If I were giving the grades based on this, roughly, if this were the end of the course, let me call it out. I'll go through those. Okay, got Wang, Rambarath, Stepanov.
I'll take them.
Balanides, Mitchell, Albina, Stewart, Gosin, Thomas, Alvarez, Mueller, Lambro, Yakovos, Valius, Gillette. That's it? Okay. Okay, so roughly speaking, if this were towards the end, these would be A's. The ones in the middle would be B's. The ones down here would be C's. I don't know about these, depends. And where the borderline is between A minus B plus or B minus C plus, I don't know. Depends later on other things. Okay. Valius. Okay. I know you're in here. There you are. Also, if I were to grade these again, except for the 100%, of course, the grades wouldn't turn out to be exactly the same because there's always some judgment, some noise in there. But you can basically see where you are. But the question for you is not how you did on this, but whether or not you understand it, because there's lots of reasons you could have made mistakes. And the important thing is to understand the material at the end of the course, not at the beginning. And at the end, there'll be, as we go along now, the course is going to sort of change its character, because up to this point, everything has been elementary in the sense that the mathematical level has just been high school algebra. So now we're going to start using the stuff, or soon we'll start using the stuff from homework 0, which involves the calculus. So in some sense, the course will get harder because it'll be more advanced, but in some sense it'll get easier because it'll be more algorithmic. So you don't have to be as clever, you just have to do what you're supposed to do. And the hard principles, I think, have already been covered. And by the end of the course, maybe these things will come back and will make sense. So when I go over the exam, if your point of view is, damn, I could have got that, then fine, stay in the course. The actual grade here will not be very important, although it will count a little bit. It's like a homework. On the other hand, if when I go through this you have no idea how to do this or what I'm talking about, then you should drop the course. Okay, so before I go through the exam itself, any questions? Okay, so let me erase this. So going, gone, right? Yeah, question?
I can't tell what my grade is and it's not up there, so, well, what I see.
It's not up here?
They got either 25 or 26, but it's not up there.
25 a.m., 125. That's probably you. So don't tell me your social security number because this is all secret, right? Have to protect everybody's identity here. So nobody knows who he is. Okay. So it says a pair of identical looking dice, consider a pair of identical looking dice, and you already knew that that was going to be, the question was going to be based on that, so you had to try and decide what kind of questions I could ask. And an obvious one, I think, is that the dice are not necessarily fair dice. So you might have guessed that. Otherwise, there really wasn't anything that would be different from anything else we've already done. But in any event, even if you didn't think of that in advance, you should have been able to figure it out once I gave you the information. So it says one of the dice is ordinary, which means it has 6 equally likely faces numbered 1 through 6. The other is loaded, which means that the face that ordinarily has a 1 has a 6 instead. That is, the loaded die has 2 6s on opposite faces, and of course no 1s. And then it says, suppose that the pair of dice is rolled once. So you have to worry about what the pair values are. So let's formulate this reasonably carefully. So first of all, it's going to be a sample space. And so let me call the dice, so I'll say this, assume. And we're going to have 2 dice, and I'll call their values XL for loaded and XF for fair. Okay, so these are the 2 random variables then, and one corresponds to the loaded die. Can I get some more ink? These things seem to be wearing down here. So we have a loaded die and a fair die, and we'll assume that they are independent. In other words, the individual dice are independent, so that if you knew the value of one of them and you know which one it was, then that tells you nothing about the value of the other. So that's an assumption. Of course, everybody made that assumption. Nobody worried about it. Even if you didn't state it explicitly, I think you made it. There was nobody who argued and said, I can't solve this problem because I don't know whether or not the dice are independent. Then what that means is this. It means that the joint probability that the fair die equals I and the loaded die equals J is equal to the product of the probabilities that the fair die equals I times the probability that the loaded die equals J. That's what you mean when you say they're independent. And then we have to say what these probabilities are. And so we're told that the fair die is the ordinary thing with 6 equally likely faces. Actually, what it says is one of the dice is ordinary. Yeah, 6 equally likely faces numbered 1 through 6. So that means that the probability that in a single roll of the fair die, I get the value I, that would be equal to 1/6 for I equal 1, 2, up to 6. And it says that the other die is loaded, so let's call that the probability that XL, the loaded die, equals J. And now by loaded, what that means is that, in this case, as it's defined, that means that the values it can take are 2 through 6, and the 6 occurs twice, has 2 faces, and the 1 that never occurs at all. So then the obvious way to do this, to model this, and everybody seems to get this part right, is to say, well, what that means is that the probability that if J is equal to 6, the probability of rolling a 6 should be 2/6, because there are essentially 2 points in the sample space that correspond to a 6, and for J equals 2 through 5, J equals 2, 3, up through 5, the probability should be 1/6, and of course for J equals 1, the probability is 0. I didn't write that. And notice, of course, that that 4 of these plus 1 of these adds up to 6, 6 through 1. So this is essentially the statement of the problem. Now, from that I can make my sample space. Let's try this one. So I'll indicate my sample space as usual. So die number, the fair die, could have values 1. Let me try it in blue. Okay. Purple works. So we have 1, 2, 3, 4, 5, 6. So let me call this x of f. 1, 2, 3, 4, 5, 6. And then there is x of L, the loaded die. And it can take values 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So,
6, 2, 3, 4, 5, 6.
Is that
6, 2, 3, 4, 5, 6.
Well, I'm putting a 1 in here, but it's going to have probability 0. So I'm just going to draw the diagram and then recognize that these points actually don't occur, but these points do. So these are the points that can actually occur. I could have left them out and not drawn them in there, but I'm trying to make this consistent with all the other cases we've looked at. So what I'm doing is I'm taking these 36 points, and I'm reassigning the probabilities. So I'll put little x's here. So what that means is the ones with x's, those are equivalent to 2 points. And the little dots are the usual with 1 point, and these guys never occur, the guys in the first row. And so, for example, the probability of the fair die being a 1 and the loaded die being a 6 would be equal to the product of 1 6 times 2 6, which is 2 over 36. So this point right here is probability 2 over 36, 2 over 36, and so forth for this row. All of these others have probability 1 over 36, except these which have probability 0. And so all of those points then are going to add up, their probabilities are going to add up to 1. Okay, so this is the setup. And actually this is, in some sense, the most creative part of the problem, because the rest of it is straightforward. You just answer the question if asked. But you're assuming independence of the dice. Of course, there's no other reasonable assumption to make, but that's part of the model. And you are assuming that the loaded die, the fact that it's loaded, what it means by having 2 different 6s and no 1s essentially means that the 6 occurs twice as often as the other numbers, and the 1 doesn't occur at all. Okay, so this is the setup. And remember, in probability, what you do is you write out a sample space which describes the events that you consider can happen. You're already eliminating other things, like you're not worrying about the phases of the moon or anything like that, or the dice vanishing into the air or standing on a corner or something of that sort. So these give you, these points, this diagram gives you the set of possible events, and the points are, in a sense, the atoms, or the smallest events that can occur, and you have to assign probabilities to those, and there's no mathematical way to assign, no algorithm for assigning the probabilities. That's part of your insight, your model. And in some cases that can be very difficult, but in this cases like this is very simple. There's only, the only reasonable way to do it is simple, and everybody did that. Nobody seemed to have any problem with that. Okay, so there's our setup, and now we want to answer these various questions. Okay. So question 1, the question is, it says, suppose that the pair of dice is rolled once. Find the probability that the face value of the loaded die will be 3. We'll call this P1. And that's the probability that the loaded die will be 3. And that, of course, is 1/6, because you already stated that right here. Probability the loaded die has a value j, where j is between 2 and 5 is 1/6. And if you look over here at this diagram, you could go to the set of points that corresponds to to the loaded die being 3, and that's right here. So this corresponds to the loaded die having the value 3. And if I add up those probabilities, since they are all 1/6, let's see, this would be 1/6 plus 1/6 plus 1/6 plus 136 plus 136 and so forth all the way across. That would be 6/36 or 1/6. Okay? That's called the marginal distribution. If I add these up, because then I can write the probabilities in the margin of the paper. So if I added up these probabilities across the rows, that would give me the marginal distribution of XL. And if I added the column, that would give me the marginal distribution of XF. Fair done. Question number 2. P2. What's the probability that the sum of the dice, which is the value of the fair die plus the value of the loaded die, is equal to 8? So now I go over here to my diagram, and I'll draw the set of points. I'll indicate the set of points that corresponds to the sum of the dice being 8. And as you can see, that corresponds to 2, 6, 3, 5, and so forth. So I can draw a picture like this. So this set corresponds to XF plus XL equal 8. So all I have to do is add up those probabilities. So this would be 2/36 plus 1/36 plus 1/36 and so forth. So it's 2 plus 1 plus 1 plus 1 plus 1, which adds up to 6. So it's 6/36. So in other words, this is equal to the sum of the probability that the fair die takes the value I, and the loaded die takes the value 8 minus I, summed as I runs from 2 to 6. And that, of course, as we just indicated by adding those things up, is 2 plus 1 plus 1 plus 1 plus 1, which divided by 36, which is 6/36 or 1/6. Most people got that right. So most people got question 1 and 2 right. Okay, question number 3. Now the question says, and of course you have to interpret this correctly, it says find the probability that if the value of the roll is 8, the face value of the loaded die is 3. Okay, so let's call this P3. And it's the probability that the value of the loaded die is 3, given that the sum of the dice, XF plus XL, is equal to 8. So that's a conditional probability. And now what you're supposed to do is just apply the formula, the rules for conditional probability. So the denominator is the probability of the event on which I'm conditioning. So that's the probability that the sum of the dice is 8. And the numerator is the probability of the intersection of the event that the sum of the dice is 8 and the loaded die is a 3. Okay, so the sum of the dice is 8, that's right here, and the loaded die is a 3, that's right here. So there is one point in the intersection, which is right here, and that's the point that corresponds to the fair die being 5 and the loaded die being 3. So the numerator is the probability of the intersection, which is the probability that the fair die takes the value 5 and the loaded die takes the value 3. Obviously, if the loaded die is 3 and the sum of the dice is 8, then it must be true that the fair die has the value 5 and the loaded die has the value 3. And conversely, if the fair die is 5 and the loaded die is 3, then the sum of the dice will be 8. So you could do this without drawing this diagram, or you can draw the diagram and see immediately that the intersection of that set and that set is a single point right here. Okay, now you just plug in the numbers, which you already know. The probability of this particular point is 1 over 36. The probability of the in the denominator is P2. You've actually just done this one, and its value is 1/6, or 6 over 36. The 36's cancel, and the answer is again 1/6. Now, I had a little bit of trouble with making up this exam because, on the one hand, I think that this is a straightforward generalization of what we've done before, so it's a good question in that sense. Not exactly the same, but same principles. On the other hand, it's possible for somebody who has no idea what's going on to just write 1/6 for everything, because those were the answers that you would have gotten for some questions if the dice were not weighted, if one of the dice was not weighted. But I assume that all of these questions are trade-offs, because you always have to ask yourself, I don't want to write a question that the smart people are going to get wrong and the dumb people are going to get right. You don't want to do that, but sometimes you can't prevent that. But in any event, I assume then, as far as this question goes, that everybody who got it right for the right reason. So, everybody got this right, most people got this right, and many people got this right. Is there a question? Yeah.
Sir, for question 3, you do not consider getting like something other than 8, right?
Do not consider what?
Like if you roll the dice, you could have gotten a 6 and a 1, for example. That's not.
Well, you could get if you get a 6 and a 1, it doesn't add up to 8.
Right, but the fact is when you roll the dice, that's a possibility.
Yeah, it's in the sample space. Sure.
So I can see how if you roll the dice and get 8, right? And then if you roll the dice and get 8 with the loaded one being 3, I can't see how the possibilities are the same. It seems like the possibility of getting 8 is greater than the possibility of getting 8 when the loaded one is 3.
The possibility of getting 8. These points represent the ways it's possible to get 8. The fair could be 2, and the loaded could be 6. The fair could be 3, and the loaded could be 5. 4, 4, 5, 3, 6, 2. Those are the possibilities. Now, the probability is the sum of the probabilities of each of the individual points, because those points are mutually exclusive and they add up or cover this whole set. Now, the probability of this one is 2 over 36. 1 over 36, 1 over 36, 1 over 36, 1 over 36. You add that up, that's 6 over 36. Okay, so that's what we have here, 6 over 36, or 1/6. It's the same thing as the denominator there, 6 over 36. Now, what you want to calculate for this question is you want to calculate the ratio of the probability of the intersection of these two events to the probability of the event in the denominator. Of course, the event in the denominator we just calculated. That's P2, that's 6 over 36. Now, what about the intersection? The intersection is the probability that both of these occur. In other words, the sum is 8, which means that we must have a point in this set, and the loaded die is 3, which means we must have a point in this set. Well, there's only one point that belongs to both of those that's in the intersection. The probability of that one point is 1 over 36.
Right, so therefore, you're only considering the situations where you get 8. You're not
Yeah, that's what it says. That's exactly the statement of the problem. It says,
I'm saying if you roll the die and get 8, then you're part of the loaded die. So I was thinking that that's a possibility of getting the loaded die being 3 and the fair die being 5.
that's what would have to happen in order for this
So I thought that was what you were asking.
Well, you were not interpreting it correctly as a conditional probability. The question isn't what's the probability the loaded die is 3. The question is if the value of the roll is 8. So by telling you that, I'm already eliminating every possibility except the possibilities corresponding to the points in this set. That's the condition. So if the sum is 8, then what's the probability that the loaded die is 3? So the first thing you have to do is you have to go from the words to the proper mathematical formulation.
Right. I did that first, but then I was thinking it couldn't be correct because then the two possibilities, number 1 and number 2, it seems like number 2 should be higher than number 3.
Well, they could be, but they don't have to be. If you remember, we did this for the case in which the dice were fair, both dice. And then I asked for the probability that the sum of the dice was a 7, and it was 1/6. And then I asked for the probability that the one of the dice had any particular value given the sum was 7, and it still turned out to be 1/6. All that's happening in this problem is it's the same question, except that things are shifted slightly because I'm assigning a value of 2 to this point rather than a value of 1. So now this set with a smaller number of points for 8 plays the same role as this set with a larger number of points played in the other case. There are more points here in the case of the sum being a 7, if I consider this as a possibility, but the probabilities of those points are all 1/6, whereas in this case there's one less point, but one of the points has twice as much value. So there's no intuitive way that you would know that these are the same or different, but they don't have to be the same or different. In fact, what this shows is that this event and this event are independent of each other because you get the same probability whether you have the condition or not. I didn't ask that, but that's what it shows. Yeah.
Well, I guess in this question the confusion was that like I calculated the probability of the roll, which is like 1/36, and maybe I misinterpreted the question. Actually, it's asking the face value of the loaded die. I mean, it's 3. It's just it should be 1/6 because you're only considering like the one die, right? And getting 3 is 1/6.
Well, no.
There's no possibility of getting a...
No. It turns out that the probability is 1/6, but that's because it turns out that restricting your possibilities to the cases where the sum of the dice is 8 does not affect the probability of the loaded die. It just turns out that way. That's because, having made this calculation, I find that this event and this event are independent.
Yeah, but doesn't matter if the value of the roll could be anything. The value of the roll could be for example, 6. The probability would remain 1/6.
That's right, in this case. But if instead of saying that the condition was the sum of the dice is 8, I had said the sum of the dice is 9, that would have made a difference. Just like in the case where the dice were not biased, the one I did in class, the sum of the dice being 7 didn't tell you any information about what the components of the sum were, but the sum of the dice being anything else did. So in this problem, the diagonal that sums to 8 plays the same role as the diagonal that sums to 7 in the problem in which the dice were unbiased. In other words, the principle is the same, but of course there's a slight difference, otherwise I'd just be asking exactly the same question I did in class. So the point here is to see whether you understand the principle. Okay, but you didn't really have to understand anything in a sense in order to do it, because once you read the problem correctly and recognize that what I'm asking for is this conditional probability, the rest of it is formula plugging. And the fact that the answer turned out to be 1/6, that at first glance is somewhat surprising, but it could be any number, it doesn't matter. Okay? So a lot of people got this right, but a lot of people got this wrong. But now, having seen explanations, obviously that's the answer, right? I mean, anybody disagree with that? The way you have to look at this is that you may not see it well enough, especially under test conditions, to get the problem right. But after having seen it explained, if it doesn't make sense, then you're in trouble. And your view should be, oh yeah, of course, now I understand. I hope. Yeah.
Maybe they would understand it better if you replace the 6 with 1 instead of doubling the probability, because I think the majority of us saw it that way. Maybe that.
But the 6 is not a 1. I mean, I can't replace this with a 1.
Well, what you're doing is you're replacing the 1 on the loaded die to 6, right?
Well, no, what I'm doing is I'm writing these probabilities, but instead of writing 1/36, 1/36, and so forth,
No, I understand what you're doing, but
I could leave that 2 out.
yeah.
This 2 just indicates that the probability of this point is 2 over 36. But I didn't write the 36 in each case because every one of these points has a denominator of 36. So every point in the top row has probability 2 over 36. Every point in this row has probability 1 over 36, 1 over 36, 1 over 36, 1 over 36, 0 over 36. So I could either write out the probabilities, or another way to look at it is to simply say that this point right here appears twice. I'm just weighting it. I'm just doubling it. But you wouldn't even have to draw this diagram. And if you look at this, the diagram is just an aid for thinking. All this says is that if I want to calculate this probability, what I have to do is I have to add up the probabilities of all the events, the elementary events, that correspond to that event. And that just says, well, that's the sum of all the probabilities such that that value and that value adds up to 6. Adds up to 8. So I don't have to draw. In fact, usually I don't draw these diagrams. If its diagram is in complicated problems, you can't draw diagrams. And in really simple problems, you don't need diagrams. So it depends. It's only in the middle case that I draw diagrams. So something like this, ordinarily I wouldn't even draw a diagram. I just think this way and write it down that way. So this is a more mathematical way of looking at it. The diagram is just an aid. Okay, but if I had 3 dice, the diagram would be useless because then I have to draw a 3-dimensional picture. If I had 4 dice, forget it.
Why can't you use Bayes' rule?
I don't know. It's not a...
It's saying that when you're dividing by the total sample space, it's all the doing what the whole roll is an 8, but it's also including the little guy. It's also included to.
Bayes' rule is just a conditional probability,
Right.
but it writes these probabilities in a certain form.
Right.
Now you can write them any way you want, as long as you can calculate the stuff in the numerator and denominator and do it correctly. It should give you the same answer.
It should have been the same answer.
Has to be the same answer. It has to be 1/6 no matter how you do it. The problem that worries me is that there probably were some people who wrote 1/6 because they had no idea what the answer was. So I hate to see those people get it right and people who think about it but make a little mistake get it wrong. But that's always a difficulty when you're making up a test. So, but no matter how you do it, you have to get the answer 1/6 if you're doing it right. Okay, so most people got those first 3, or many people got the first 3 right. Almost everybody, I think everybody, got this one right. And most people got this right, and many people got this right. And now number 4, most people got wrong. So 4 is where it's a little bit more difficult. Now it says, find the probability that if the face value of one of the dice is 3, the value of the roll will be 8. The difficulty here is that it says the condition, if the face value of one of the dice is 3, it doesn't tell you which one of the dice is the one that has the 3. So you have to take that into account. Okay, so now you can do that 2 ways. You can do it the intuitive way using the diagram, or you can do it the mathematical way. Do it the mathematical way, you don't have to think about it. You don't have to know what you're doing. That's the advantage. That's what mathematics does for you, is it takes problems that you don't understand and lets you solve them by simply following a formula. So let's do it the mathematical way first. Let's call it P4. Again, what you have to do is you have to formulate it correctly. So the question is, what's the probability that the fair die plus the loaded die adds up to 8, given the condition that either the fair die is equal to 3 or the loaded die is equal to 3. In other words, what it says in the statement of the problem is what you're given is that one of the dice is a 3. It doesn't tell you which one. So this is the union of the events that the fair is 3 or the loaded is 3. Okay, now once you write that down, and let me go back up here. Once you write that down, it's just a matter of using the formula. Okay, so that's going to be the ratio of two probabilities. The first one in the numerator is the probability of the intersection of this event and that event. Okay, so what's that? What's the intersection of the events that the sum of the dice is 8, okay, that's those points there, and with the fair die is 3, the fair die is 3, that's this set right here, and the loaded die is 3, that's this set right here. So the intersection of this set with this set and this set is 2 points. This one right there, or this one right there. In other words, the numerator, let me write it like this. If the sum of the dice is 8 and either the fair one is 3 or the loaded one is 3, then the only possibilities are that the fair is 3 and the loaded is 5, or the fair is 5 and the loaded is 3. So the numerator is the probability that the fair die is 3 and the loaded die is 5, plus the probability that the fair die is 5 and the loaded die is 3. Okay? Now the denominator is the probability of the event on which I'm conditioning. So it's the probability that either the fair is 3 or the loaded is 3, which is, remember we had a rule. I'll write the rule here. The probability of the union of two events is the probability of the first plus the probability of the second minus the probability of their intersection. That was one of the basic theorems of probability. We proved that using Venn diagrams. So I'm going to apply that here, where A is that the fair die is 3, B is the loaded die is 3, and AB is the probability that they are both 3. Okay, so the numerator or denominator then is the probability that the fair die equals 3, plus the probability that the loaded die equals 3, minus the probability that the fair die equals 3 and the loaded die equals 3. Okay, so all I did was plug into this formula here. I don't have to know what these things mean in order to get this answer. Then I just plug in the numbers. So that's easy enough. The numerator is 1 over 36 plus 1 over 36. That's those two probabilities right there. That's these 2 points right here. That one and that one.
I have a question, but that would be minus 0 in the denominator, wouldn't it?
No, let's do it.
The first set of probabilities minus 0. That one.
Okay, what's the probability?
Three.
What's the probability that the fair die is
That's
equal to
valid.
3?
And the other one is valid.
Well, let me write it out. I'll write this probability as 1 over 36. 6 over 36. That's 1/6.
Yeah.
What's the probability the loaded die is 3? In fact, that was the answer to the first question, right? That was also 1/6 or 6 over 36. Okay, now what's the probability that they are both 3?
That's 0.
No, the probability they're both 3 is this point right here. This one.
The question says the base value of one of the dice is 3 and the rule will be 8. So they can't be both 3.
I didn't say that they are both 3. I said that I want to calculate in the denominator the probability of the union of events. The probability of a union is equal to the probability of one plus the probability of the other minus the probability of the intersection. Okay. The probability of that is 6 over 36. The probability of that is 6 over 36. The probability of that is 1 over 36. It doesn't mean it happens. It just means that I'm applying the formula. Remember, the point of mathematics is to allow you to solve problems you can't understand. If you can understand them, you don't need mathematics. right? If you can look at a curve and find the area by just eyeballing it, you don't need calculus. Calculus is because you don't know what to do, so it tells you what to do. Now, is this right? We proved it's right. It has to be right because all I'm doing is following the rules. But I'm going to go back and interpret it intuitively. Okay, so let's see what this is. I can cancel out the 36's, and then I have 2 divided by 6 plus 6 minus 1, or 2 over 11. So the answer is 2 11ths. Yeah.
Actually, the way I saw it, the 1 should be 3, right? Any of the dice should be 3.
1 should be 3.
Like, the total should be 8, and
Yeah, one of them is 3. You don't know which one.
Yeah, let me complete first. The total should be 8, right?
Yeah, right.
And one of them should be 3.
Right,
So if the loaded would be 3, the fair would be 5,
right,
right? And if the fair would be 3, the loaded would be 5.
right.
So in my opinion, there are only like 2 possibilities.
So what answer did
Be
you
like,
get?
huh?
What answer did you get?
Like 1 by 18.
1/18th.
So there, in my opinion, there are like 2 possibilities. One would be 3, the other would be 5. The other would be 3, the first one would be 5.
Okay. Your argument is sort of okay, but it's not correct. Because if it
So it's
were,
5.
well, it's hard for me to say why, but let me go through what I think is your argument, because you've overlooked something. But if you don't believe it, what you need to do is you need to write a simulation. That is, just imagine that you're rolling these dice and keep records, and you'll see that if you look at only those times in which you got either a 3 on one or a 3 on the other, and then took the fraction of those that added up to 8, you would find it's 2 11ths. Okay, but let me make another argument, a picture, because this is just mathematics, and people tend not to believe mathematics. That's part of the problem, right? Everybody writes down formulas, like in calculus, and then they call things x, y, u, d this, they leave the d out, and they write the answer. The reason is because they're not paying any attention to what the mathematics tells them. In elementary problems, it doesn't matter because you don't need the mathematics. But in anything that mathematics is necessary for, if you neglect to interpret the symbols correctly, you don't get the right answer. Just like if you're writing a program, and the program asks you to add up some numbers, well, you could do that in your head if there's only a small number of numbers. But if in your program you give the numbers the wrong names, if you call the variables x and y instead of x and z, it's going to give you the wrong answer. So if you're following the rules, then you're going to get the right answer. And if you don't follow the rules, well, who knows what you get. Okay, so let's go back and see why the answer is 2 11ths. Okay, so now I'm going back here to the diagram. So it says the condition is that either the fair die is 3 or the loaded die is 3. So that means that either I must lie in the union of these 2 spaces right here, the 2 sets. Here is the fair die equals 3. Okay, so this is xf equals 3. And this one right here, xl equals 3. Okay, so now I've got my, let's use another color here. Okay, so now here's my reduced sample space. It consists of the points in there and the points in there. And now within that sample space, within those points, I want to find the probability that the sum is 8. And the only point that's in here and corresponds to the sum being 8 is this. So I have a sample space now which consists of those guys, and I want to find the probability of this one point in there. So what I can do then, using the reduced sample space method, is I simply take the ratio of the number of points of this point, or the probability of that, to the probabilities associated with all of these guys. Okay, now what's the probability of this one right here? Well, it's 1 over 36. What's the probability of this one right here? Let me start that again. This is 1 point. Now, when I changed from the case of equal likelihoods to the weighted die, what I said was the way I'm going to handle this from the picture point of view is I'm simply going to take the value that's the weighted value and double it. I'm going to count that 1 point as 2 points. Okay, so I'm counting this as 2 points. Now, what I want to know is the probability the sum is 8, which is, wait a minute, I made a mistake here. There are 2 ways I can get 8, that one and this one, and still be within the set. Okay, so I want to be in here or here, and I want the sum to be 8. I want the intersection of those 2 guys with this guy. That gives me this point right here, which is 3, 5, and this point right here, which is 5, 3. Okay, now how many such points are there? 1, 2. 2 such points. How many points are there in the reduced sample space? Well, there's 1, 2, 3, 4, 5, 6, 7. I've already counted that. 8, 9, and this one counts twice, 11. So it's 2 over 11. Because I don't want to rely on these kind of diagrams, because I said if I had 3 dice, then I would have a 3-dimensional diagram, and it would be useless. And of course, if I had an arbitrary number of dice, it would be arbitrarily useless. But you can see now that the answer really is 2 11s, because the reduced sample space argument says take the probabilities that are in the new sample space and multiply them all by the same factor so that they now add up to 1, and take the probabilities of all the points that are outside of that new sample space and set them equal to 0. So my new sample space consists of a union of these red circles, the boxes, the points in there, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, plus this point which counts twice. So there are 11 points in this sample space. Or looking at probabilities, the probability is twice all the others. All the others are 1 over 36. That one's 2 over 36. The 36 is, of course, canceled. So that's the 11. And the numerator is how many of those points satisfy the condition. The condition being that the sum of the dice is 8. Well, that one and that one. So it's 2 over 11. Okay, but it's important to know to use that reasoning as a check, but not your primary reasoning. The important thing is to be able to use this kind of reasoning, because you don't have to understand anything here. All you have to do is write down precisely what the question is, and then manipulate the symbols according to the rules. And that's all I did, and I came out with 2 11s. Okay on that? So this problem was intended to be more difficult than the others. As I say, most people miss this, but a few people got it right. Okay, so any questions? Everybody agree now? Kind of hard to disagree, I guess, right? Take an unfair advantage. Okay, let me erase this. As I say, if you don't believe it, write a simulation. I haven't really discussed simulation, although we're going to discuss it in detail shortly. And at that time, you can go back, and it would be easy to write a simulation and check to see if the answer really is 2 11s. Okay, question number 5. Okay, now it says, now suppose that one of the 2 dice is selected at random, and then that die is rolled 10 times. So the initial statement of the problem is that these are identical looking dice. So when I select one at random, that means I have a 50% chance of selecting the fair die and a 50% chance of selecting the loaded die. So let me introduce some notation here. Now I'm going to call x1 the value of the first roll. And I'll call x10 the value of the 10th roll. But I don't know, when I'm rolling the dice, whether it's the fair die or the loaded die. Now, question number 5 probability P5. That's the probability that the first roll, its value is 6. That's the question. The question says, find the probability that the face value for the first roll will be 6. Okay, so now this is obviously a theorem of total probability problem because you don't know which die you're using, but the identity of the die that you're using is a partition of the sample space. The die that you're using is either fair or it's loaded. So this thing could be written as the probability that the die is fair times the probability that when I roll it, I get a 6, given that the die is fair, plus the probability that the die is loaded times the probability that when I roll it, I get a 6, given that the die is loaded. Okay, it's a straightforward theorem of total probability. Total probability. And this is supposed to be easy. I mean, the first thing that's supposed to jump into your mind is, I don't know which die I'm using, so therefore I should condition on that. That's a partition of my sample space. Okay, so what's the probability that the die is fair? Well, by assumption or by statement, that's 1/2. Because when I say you select the dice at random, select a die at random, that means that the probability is 1/2. Each die is equally likely to be selected. Now, if the die is a fair die, then the probability that it's 1/6, that it's a 6 is 1/6. The probability 1/2 it's a loaded die, and if it's loaded, then the probability of a 6 is 2/6. And now simple arithmetic shows that this is the same thing as 1/4. Okay? A lot of people got that right, but not everybody. Okay, 6. P6. Now the question is, find the probability that the face value for the 10th roll will be 6. Now the insight here is that the 10th roll, let me write it before I write what P6 equals. The 10th roll has the same probability distribution, in other words, the same probabilities, same probability distribution as the first roll, or in fact any roll, or any roll.
So,
This,
what if you wrote that as your answer?
what was that?
What if you wrote that as your answer?
You wrote that as your answer? You got it right. Actually, what happened was, this answer will turn out to be, well, let me finish, okay? If I write this out then, what I'm saying is that P6, which is equal to the probability that x10 is equal to 6, that's the same thing as the probability that x1 is equal to 6. That's 1/4. So when I graded these, if you put 1/4 for both of them, they're both right. If you put the wrong answer here but wrote exactly the same number there, then I didn't check it because it's not the right answer, but I didn't take off any points. So in other words, if you wrote this thing down or put the same number for both, even if the numbers are wrong, as long as they were the same, then number 6 was correct. Because that was the whole point. Now actually a lot of people really got that right but missed it in the following sense. Because the reason it's the same is that if you have no information about the other tosses, because it doesn't say what's the probability that the 10th toss is a certain value given something else happened, all it says is I'm tossing this die a zillion times and I'm going to look at a particular time, and any particular time I look at in a statistical sense is the same as any other time.
The tosses are independent.
That's the mistake that people made, which I didn't take off credit for until the next problem, because you needed to use that. Because the tosses are not independent. This is like a case where we were sampling from an urn and we were sampling with and without replacement. And if you remember, we saw that the probability of red on the first trial and the probability of red on the jth trial were the same value, whether we were sampling with or without replacement. But if you're sampling with replacement, the trials are also independent. If you're sampling without replacement, the trials are dependent. You have to differentiate between having the same probability and being independent of each other. Okay, now if I just concentrate on the 10th roll, then it statistically is the same as the first roll or any roll, and so whatever the probability is for the first roll, it's the same for the 10th roll. But these are not independent trials, because if at any time I tell you what happened on any trial, that gives me some information as to which die I'm using. And if I know which die I'm using, that gives me information as to what the probability is when I toss it. This is actually a subtle point, but I emphasize this because this is a very important point. This is one of the things that actually experts argue about. It's hard to believe, but there's a lot of debate within the community of experts on this as to what probability means. At the low level, it's obvious, but there are basically three kinds of approaches to probability. One is the frequency approach. That is, probabilities represent frequencies. But philosophers and mathematicians don't like that because, as a matter of fact, you can never measure frequencies except in a specific case. You don't know that just because if you've tossed a coin 100 times you've got a certain result, you have no idea what's going to happen the next 100 times or next 1,000 times. There's no way to connect them unless you make some other assumption or you have some other knowledge. So, and the idea that you can repeat the experiment under these ideal conditions, that is, it's exactly the same experiment every time, an infinite number of times, of course that's only an idealization that can't actually happen. So, some people don't like the frequency interpretation, even though the reason that scientists are concerned with probability is because of the frequency interpretation.
So say we knew which dice it is, it would be independent of the first roll.
Say that again?
Say we knew which dice it is, with the first roll and the second roll would be independent?
If you knew which die you're tossing,
Just
then
the regular dice?
any die.
Yeah.
If I take a die and I tell you which one it is, then the successive tosses of that same die are independent of each other because there's no reason to assume anything else. How could they be dependent? How could there be any connection between them? Doesn't mean there can't be, we don't know. But from a scientific point of view, if you want to be rational about it, unless you want to invoke some kind of supernatural power guiding the die, then they have to be independent. But that's part of our model. On the other hand, if you don't know which die you're tossing, then the tosses are not independent because each toss gives you information. Let's take something that's more extreme. Suppose I had 2 coins. One coin is fair and the other coin has 2 heads. And I say, I'm going to select a coin and toss it, and are these tosses going to be independent? And the answer is, well, if I don't know which coin if I know which coin I've tossed, then sure, there's no effect from one toss to the other because I know which one I'm using. But if I don't know which one I'm tossing, then I look at the sequence of events up to the toss I'm talking about. Suppose that every toss up to this point has given me a head. Pretty likely that the reason I never got a tail is because I'm using a 2-headed coin. So the more heads I get in a row, the more likely it is that I'm using the 2-headed coin. On the other hand, if in the sequence, someplace along the line I get a tail, then I know for sure that I must be using the fair coin, and then after that the probabilities are all 1/2 and they're independent.
So, like, if you can't get any information from that, then they're independent.
No.
And I know that's not what the thing is, but I'm just saying it's a big problem. Since the tosses between the 1 and the 10 who gave us something about which coin it is, that's why they're...
No, but wait, you're saying independent.
Independent.
Okay, if, as in this case, there is no information, it still means that the dice are dependent because if you had the information, then that would affect the probabilities. However, you don't have the information, so the probability is not affected, but that doesn't mean that the dice or that the tosses are not independent, are not dependent upon each other. Okay? So it's incorrect to say that the tosses are independent, but it's correct to say that the tosses have the same distribution. So the probability is the same if you don't have the information. But the tosses are not independent of each other, as we'll see in the next problem.
Sir, are you saying that if this situation occurred, right, and you had two persons, one that knew what the die was, and the other one didn't, and the probabilities would be different?
That's right. In fact, let me finish what I was saying before. There are three models of probability that you could take. One is the frequency model. The frequency model is what scientists, engineers, physicists, that's what they want because frequencies are what they observe, and so they're trying to make a model of that phenomenon so that they can predict and design things. Then there's the mathematical model. Mathematicians take this and they say, wait a minute, this is all crap because these people can't think clearly, so we have to make things rigorous and precise. So then they make the model very mathematical, abstract it, remove it from reality. That has some advantages, some virtues, but it can go to extremes. And if you read probability theory for mathematicians, it has practically no relationship to the probability theory that everybody else who uses it is concerned with. It has to do with measure theory and real analysis, very complicated mathematics, and people get into very bitter arguments about whether or not the mathematicians, I'm exaggerating here, but they claim that the engineers are stupid, and the engineers claim the mathematicians have no idea about the real world, can't even tie their shoes, that kind of thing. But there's another viewpoint, which is the viewpoint that probability really represents information. And that's the viewpoint that the so-called Bayesians take. And the truth, that, in my opinion, that's probably true. But the way you think about things when you calculate and the way you think about things as a philosopher are different. So my view is that when you're talking about probability, when you define your sample space and you assign the elementary probabilities, you're making some assumptions, which are the assumptions that engineers make because they want to use this stuff. And the answers are only as good as those assumptions are. But then in making those assumptions, you are using some external information. Like you're using the idea, if you're tossing dice, that, well, every face ought to occur as often as every other case, because why not? There's no other reasonable thing to say. But that's an assumption. And if you say that dice are independent, well, that's the only reasonable thing to say, but still, it's an assumption. Now, if you have additional information, that information then should be incorporated into the problem. And that then changes the probabilities. So probability reflects frequencies that you would observe based on the appropriateness of the information that you're using to make the model. So in this case, we have only the information that's stated. These are simple problems. And now, in problem number 7, I give you some more information. And the question is to see whether or not you recognize that. Of course, it's not really that tricky because there was exactly the same kind of problem in the sample exam. It was just in the context of coins instead of dice. Okay, so now number 7 is what the question is. And 7 and 4 were the questions that most people missed. But several people got them right. Okay, P7. Now the question is, what's the probability that the 10th roll is a 6 if you know, given that the first roll is a 6? So intuitively, if you know the first roll is a 6, that means you're twice as likely to be using the biased, the loaded die, as you are the fair die. Because the loaded die has 2 6s and the fair die has only 1 6. So intuitively, you know that the probability now that the 10th die, that the 10th roll gives you a 6 should be not a quarter, because now I have more information. Here I didn't know which die I was using. Here I don't know which die I'm using, but it's more likely, twice as likely, that I'm using the weighted die, the loaded die, than that I am using the fair die. But I want to take the mathematical point of view, the simple point of view, because I want to explain it as if I couldn't understand the problem. So I just use the definition of conditional probability. The denominator is the probability that x1 is equal to 6, and the numerator is the probability that jointly x10 x10 is equal to 6 and x1 is equal to 6. So now I got to calculate those things. Well, we already know the probability that x1 is equal to 6 because we calculated that right here, the quarter. But what's the probability of this event right here? So now I'm going to use the theorem of total probability. I'll say the probability of this event is the probability that the initial selection of the die gave me the fair die times the probability that x1 is equal to 6 and x10 is equal to 6, given that I'm using the fair die, plus the probability that I am using the loaded die times the probability that x1 is equal to 6 and x10 is equal to 6, given that I'm using the loaded die. So all I did was apply the theorem of total probability to the numerator to get this in a form that I can calculate. Okay, now, what are these probabilities? The probability that the fair, well, let's do the denominator first. The denominator has a 1/4. Now, what's the probability that I'm using the fair die, that I selected the fair die? Well, it was 1/2. Now, if I selected the fair die, what's the probability that these two particular rolls with the same die will give me a 6? Well, the probability that I get a 6 on the first roll is 1/6. The probability that I get a 6 on the second roll with the same die is 1/6. So it's 1/6 squared. Because if I know which die I'm using, then the rolls are independent of each other. There's no way that unless there's some supernatural force here controlling the die, that the outcome of any trial is related to the outcome of any other trial once I know exactly which die I'm using. On the other hand, the probability that I'm in fact using the loaded die is 1/2. And then if I am using the loaded die, the probability of getting 2 6s in 2 separate trials would be 2/6 times 2/6, or 2/6 squared. And now it's just arithmetic, and the answer turns out to be 5/18. Okay, let me do it another way. Now I'll do it the way that uses the fact that since I know that I got a 6 the first time, I'm twice as likely to be using the loaded die. So I'll say also. So here's a different way of looking at it. The probability that the die is loaded, given that when I roll it I get a 6, is equal to, the denominator is the probability that I get a 6. And the numerator can be written as the probability of getting a 6 given that I'm loaded times the probability of loaded. So all I did was rewrite the numerator just like you do in Bayes' rule. And the denominator, I didn't need Bayes' rule, I didn't need to write it out because I already know what that answer is. Okay, now what are those probabilities? The probability of getting the loaded die is 1/2. And the probability, if I had using a loaded die of throwing a 6, is 2/6. The denominator here we already know is 1/4. And so by arithmetic, this answer turns out to be 2/3. Okay, but we already know that intuitively, because if you got a 6 the first time, since there were 2 6s in the loaded die and 1 6 in the fair die, it's twice as likely that you were using the loaded die. So in other words, therefore, on the 10th trial, the probability that the die is loaded is 2/3, and the probability that it's fair is equal to 1 minus 2/3, or 1/3. Okay, so now let me go back and calculate P7 using the theorem of total probability, just like we did in calculating P5. The probability that the 10th trial gives me a 6, if the first one gave me a 6, is the probability that I am using the fair die times the probability that x10 equals 6 given fair die, plus the probability I'm using a loaded die times the probability x10 equals 6 given the loaded die. The probability of the fair die is now not 1/2, but is now 1/3. And if I'm using the fair die, the probability of a 6 on a single trial, the 10th trial, is 1/6. The probability that I'm using a loaded die is now not 1/2, but 2/3. And if I'm using a loaded die, the probability of a 6 on a single trial is 2/6. And now by arithmetic, that turns out to be 5/18, which is exactly the same as you got by the other argument. So they're equivalent. They're equal. Okay, we got about a minute left, and I came across a quote recently in a probability book, and it was talking about exactly this idea of recognizing that probability represents information, and that it's much better if you don't know something to say you don't know it than to write down something that's stupid. So here's a quote from Thomas Jefferson, 1781. I don't know if this is in the Declaration of Independence or not, but it should be. It says, "Ignorance is preferable to error, and he is less remote from the truth who believes nothing than he who believes what is wrong." Okay, so that's my word for the day.